Dear students, having studied about covalent bond, today we are going to look at another interesting type of bond, that is ionic bond. We will also compare the behavior of ionic and covalent bonded materials so that you can understand the different material properties in real world based on the type of bond they form. In the case of covalent bond, you already know that when two highly electronegative atoms come together, they share their electron to attain stable electron configuration. Through this sharing, covalent bonds can form small molecules like O2, H2O, N2, etc. They can even form solid covalent networks such as diamond and silicon. One interesting thing to remember is that the number of electrons shared between atoms determine how strong the bond is. For example, in the case of H2O, there is one oxygen atom at the center. This has two electrons at the first orbital electron shell. In the second, it has 2, 3, 4, and 5 and 6 electrons. To attain stable electron configuration, this requires 8 electrons. So in the case of H2O, it shares one electron with H because which has already one electron, and it attains stable configuration when it gets two electrons. So it shares with H and it shares one more electron with another H. So what happens? H gets two electrons in its outer shell, and this H also gets two electron, and this oxygen gets 8 electron at outer shell. So this is a stable configuration. In this case, you can see it is sharing only one electron with one element. In the case of O2, where two oxygen atoms are shared, so in this case, so this has 6 electrons. Of course, in the first cell it has 2, and one more oxygen comes, 2 electrons it has, outer it has, again 6 cell electrons. So what happens? This supposed to be in the same size, okay? So when it comes closer, this shares these two electrons each. So oxygen becomes O2. So this has 4, 6 and 2. So 8 electrons. This oxygen gets 8 electron. The other oxygen also gets 8 electrons. So it is a stable electron configuration. So O2 where 2 electrons are shared. In the case of N2, nitrogen, it requires 3 electron outside because it has 5 electrons already. It has 5 electrons. It requires 3 more electron to become stable. So what it does is it shares 3 electron with neighboring nitrogen. So it has 1, 2, 3, 4, 5, 6, 7, 8 electrons. So both nitrogen has 8 electrons. So this is a triple bond. So this is a single bond where oxygen and hydrogen are bonded with 1 electron. This is a double bond where oxygen and oxygen are bonded with 2 electrons sharing. And this is a triple bond where nitrogen and nitrogen is bonded with 3 electrons sharing. More electrons they share, the bond is more stronger. So this is a weaker bond relative to other two bonds. So more electrons they share, more stronger the bond is. Now let's have a look at the electrical behavior of covalent bonded materials. If you look at covalent bonded materials, the main behavior is that two highly electronegative atoms come closer and they share electrons to attain stable electron configuration. In this case, all the shared electrons are tightly held by the adjacent atoms, and these electrons cannot move freely. These electrons are locked and it cannot move freely. So, in any covalent bond, the electrons are completely held within the atoms, making it one of the strongest bond among all types of chemical bonds. Keep in mind, I'll repeat again, covalent bond are the strongest bond among any other bonds available. Now, let's talk about conductivity of covalent bond. Any material is its capability to move electron from one point to another point. If I give an electron this side, I must be able to take an electron out from another side. But the problem with covalent bonded material is that their electrons are so tightly held, they cannot move. That's the reason most covalent bonded materials cannot conduct electricity except graphite, which we have already discussed earlier and understood the reason for its special behavior. So materials like wood, plastic, rubber are poor conductors of electricity because their electrons are completely held in place. There are no free electrons to move. Then let's move on to the next topic, impact of heat. Before understanding this, you must recall that covalent bonded materials can have large molecular structures. For example, if you consider a plastic or wax, each wax molecule is a long chain polymer. A billion and billions of such molecules join together to form a large structure. If you consider sugar as an example, this is a simple sugar molecule and there are multiple sugar molecules joined together, and you can see all the sugar molecules are joined together and became a bigger sugar crystal. So you can understand that any material, right from sugar, any polymer, long chain polymer, the reason why we to look it as big, it is not because of this is made of one single molecule. This is made of combination of billions and billions of molecules. So what we must understand is that under scanning electron microscope, we can see that each tiny shape is a single molecule. In the case of wax, you can consider it as individual wax molecules. All these wax molecules are neatly arranged in a solid. Therefore, in a covalent bonded material, there are millions of such molecules. The covalent bond exists inside each molecule, holding the atoms together. But between different molecules, there are only weaker intermolecular forces, not covalent bonds. Between these molecules are weaker molecular forces, intermolecular forces, but these are all not covalent bonds. These are all intermolecular forces between molecules. That's why at room temperature, the wax is solid because the intermolecular forces are strong. When we heat wax, the molecules begin to vibrate, and these vibrations weaken the intermolecular forces. And once these forces are broken, the molecules flow away. They can move freely, and that's why wax melt. A similar behavior can be seen in water. In water, molecules are held together by hydrogen bonds. In ice, these hydrogen bonds are strong and hold the molecules tightly, giving it a solid structure. Molecules are held very tight because it has very little energy, and the hydrogen bond makes hexagonal structures in the water molecule because of its shape. When we supply heat to ice, the hydrogen bonds weaken and the molecules begin to move. This is how ice turns into liquid water. If we keep adding heat further, the bond between the molecules, which is hydrogen bond between the molecules, break and each molecule escapes. This is evaporation and the water becomes water vapor. In all these cases, you must clearly understand that heat is not breaking the covalent bonds inside the molecule. In all these cases, you must understand the heat is not breaking the covalent bond inside the molecule. So if you heat water molecules, this intermolecular forces breaks, but between O and H, the covalent bond does not break. So melting of covalent bond does not mean that covalent bonds are broken. It only means that molecules are separated from each other because the intermolecular forces break. So melting is not breaking covalent bonds. Covalent bonds are extremely strong and normal heat cannot break them. Only at extremely high temperature can covalent bonds be broken. Under ordinary conditions, melting happens only because of the breaking of intermolecular forces, not the breaking of covalent bonds. Let's see another interesting property of covalent bonds. The image on the left shows a diamond and the one on the right shows quartz, the material used to make glasses. Now both may look like stones in their raw form, but why is diamond so special compared to quartz? Let's look at their molecular structure. Let's look at the molecular structure. In the case of diamond, it is made up of 100% pure carbon. Each carbon atom forms 4 bonds with neighboring carbons. This creates a solid 3-dimensional network that extends throughout the entire structure. Because of this uniform and perfectly bonded carbon network, diamond becomes one of the hardest natural material known. Also, forming such a perfect structure of pure carbon with all 4 bonds uniformly arranged is a very rare process in the nature. That's why diamonds are so special and valuable. Now, if you look at the quartz, it's made of silicon oxide, 2 oxygen molecules bonded with 1 silicon. Silicon is just like carbon, can also make 4 bonds, but instead of bonding with other silicon atoms, it bonds with oxygen atoms. The structure of quartz is similar to diamond, but the atoms involved are different. The silicon oxide bond is weaker than the carbon-carbon bond in diamond. Because of this, glass which is made from silicon oxide can be melted when heated to high temperature. Melting any material means you are allowing the atoms or molecules to move freely, but it doesn't mean you are breaking all the covalent bonds. In the case of silicon oxide, that is glass, each SiO2 unit is one molecule. When heated, we don't break the silicon oxide bonds inside the molecule, but rather the intermolecular forces between SiO2 units break, allowing the molecules to move relative to one another. That's why glass can melt and flow when heated. However, in the case of diamond, the entire structure is one single giant molecule, where all the carbon atoms are covalently bonded throughout. So, to melt diamond, you would have to break every single bond at the same time, which require huge energy. That's why diamond remains so special. It's pure carbon, perfectly bonded in all directions, forming a single continuous crystal that cannot melt under ordinary conditions. Whereas glass may look like diamond, but this is made of combination of many SiO2 molecules. So let's recollect all the important points that we have discussed about covalent bonds. The covalent bond is the strongest bond among all types of chemical bonds. In a covalent bond, electrons are shared between atoms, and these shared electrons held very tightly. Because of this, no free electrons are available to move, and hence most covalent materials do not conduct electricity. However, there is one exception: graphite. Graphite is the only covalent material that conducts electricity. This is because in graphite, each carbon atom bonds only with three other carbon atoms, forming three covalent bonds. The fourth electron in each carbon atom remains free, and these free electrons are able to move throughout the layers, allowing electric current to flow. That's why graphite is special. Next, diamond is another remarkable example of a covalent bonded material. It is made of pure carbon, where each carbon atom forms four covalent bonds with four other carbon atoms, creating a solid three-dimensional network. If you look at a diamond, the entire structure, no matter how large it is actually one single molecule made of interconnected carbons. Because of this perfect and continuous bonding, bigger diamonds are very rare and extremely special. Finally, when we apply heat to covalent bonded materials, most of them melt. But this melting does not break the covalent bonds between the atoms inside the molecule. The heat only breaks the intermolecular forces, the weak attraction between different molecules, allowing them to move freely. So remember, melting does not mean breaking covalent bonds. It only means breaking the weaker bonds between molecules, while the strong covalent bond inside each molecule remain intact.